Question 21. A student investigates the acceleration of a trolley. The trolley is released from a fixed position and accelerates. The accelerating force is provided by the weights attached to the trolley with string. Acceleration is measured using the light gate and data logging equipment. Look at the results from the experiment. Part A. The student has made 2 mistakes in the results table. Identify the 2 mistakes and suggest corrections to them. So let's see what we've got in our data table. Force, newtons, some numbers here. Acceleration, should be a unit of measurement here. Got some numbers. This looks a bit like an odd one out. What's different? Aha! The other ones all have 1 decimal point, but this one does not. Or rather, the others are done to 2 significant figures, and this one's only done to 1 significant figure. I think those are our 2 mistakes. So mistake 1, no unit of measurement for acceleration, and to correct it, well, put it in. Give unit, and just to show that we know what we're talking about, the unit of measurement for acceleration, or at least the standard unit, is meters per second squared. Mistake 2, acceleration for row 3, 1, 2, 3, is only given to 1 sig fig, others are 2 sig fig, so give all data to same precision, 2 sig fig or 1 decimal place, whatever they've used there. Question 21b. The student plots the results on a graph. 1 point has not been plotted on the graph. Plot the missing point on the graph. Let's get our data table out again. The force for 1 Newton is there, 2 newtons, 3 newtons, 4 newtons is missing, 5 is at the top there. So the data for force 4 newtons is the one that we want. The acceleration is 5.7. Let's get our sharpened pencil out and make sure we get 5.7 correctly. Looks like there's 10 squares between each of our main indicators. So 5, 10 squares, then 6. So each little square is 0.1 meter per second squared. So 5.7, 1, 2, 3, 4, 5, 6, 7, or rather go back 3, 5.9, 5.8, 5.7. That's where our 5.7 is. Our force was 4 newtons, so it goes on the main line. There we go. 5.7, nice and small there with a sharp pencil. Question 21b, part 2. Describe the relationship between the 2 variables on the graph. Well, they've kind of given part of this away with a nice straight line of best fit, which goes to a 0, 0 origin. So this is a proportional relationship. Force is proportional to acceleration. You can get 1 mark for saying that it's a linear relationship, but remember it's not just a linear relationship, as this one goes through 0, 0. When one variable increases, the other variable increases by the same proportion. So it's not just linear, it is proportional. That's our 2 marks there. Question 21b, part 3. Calculate the gradient of the graph and use this to determine the mass of the trolley. Now, before I do any kind of maths here, I'm just going to find out the gradient of the graph, because, well, they've told us to do it. It's important to do the gradient from the line of best fit. So don't do gradient using data points. Get my ruler out and make a comically large gradient triangle on our graph. Luckily, it looks as if I can just go right to the edge of the graph paper here. There we go. 1 line there, 1 line here. Change in y is 5 minus 0, so just 5 newtons. And our change in x is 7. There we go. Let's keep our decimal points in there. We've got that precision. So gradient equals delta y over delta x. Change in y over change in x equals 5.0 over 7.0. 0.714 newtons per meter per second squared. If you're interested, not that we need to know the units of measurement for the gradient, but how are we going to use this to find the mass? Well, some of you may have noticed already, this is a force and acceleration graph where they're proportional. This is Newton's second law, so Newton's second law. F equals ma. This equation here tells us that if we were to plot force against acceleration, we'd have a straight line of best fit where the gradient is the mass, which is rather handy for us. In fact, that's why they put force on the y-axis and our acceleration on the x-axis for us. Y equals mx plus c is the general equation for a straight line graph in maths. If f is our y values, a is our x values, kind of confusingly but rather apt, is our mass is equal to m, which is the symbol for gradient. The plus c is 0 in this case because our y-intercept is 0, so our gradient is the mass straight away, 0.714 kilogram. Question 21b, part 4. The actual mass of the trolley is lower than that found in the experiment. Suggest 2 reasons why. Use ideas about forces and energy in your answer. If we have a look at the experimental setup once again, it's important to note that there's a lot of assumptions going on. The accelerating force is provided by the weights attached to the trolley with a string, and presumably the weights themselves are equal to the force pulling that trolley, or at least that's what's assumed. In the picture also, the trolley is here, the thing that we're trying to find the mass of, but it's attached to this string. In a perfect world, this string wouldn't have mass, but unfortunately, it probably does have some mass. So the weights are not only pulling the trolley, but also this string here too. We've also got this pulley, which in a perfect world would have no friction, but alas, some energy is probably being dissipated here. So the gravitational potential energy of these weights as they fall, providing that force, is probably not being transferred 100% to that trolley. So we've got a lot of things that we can talk about. Bear in mind our question asks for 2, so try to pick 2 really good ones, but I'll write down some of the ones that I've just spoken about. String has mass, so force of weight is acting on trolley and string, by which I mean not just the trolley. Pulley has some friction, so not all of the GPE, gravitational potential energy, of those weights is successfully transferred to the trolley. Speaking of friction, we could also talk about the friction in these wheels. There's going to be some energy transferred there, which isn't directly going into the kinetic energy of the trolley. So the wheels will heat up ever so slightly, just like this pulley will. And our mark scheme also allows us to talk about the use of this card through the light gate. This light gate is a timing light gate, just like the ones I talk about in that video. So in order to find out the velocity and therefore the acceleration of this trolley, the student must have taken some measurements of the width of this card to use with the time given by the light gate. And if they made any errors there, they could have an incorrect velocity and therefore acceleration. So we could talk about how our mass, which we got from the gradient of the graph, relies on having accurate acceleration and force measurements. So if we don't have accurate velocity measurements by not measuring the light gate card accurately, we're not going to have a accurate mass at the end. Question 21b, part 5, suggests 2 ways the experiment could be improved. For this particular question, we need to have improvements for the reasons we've given in our previous question. So in this context, string has mass, so the force of the weight is acting on a trolley and the string, not just the trolley. Our improvement could be to have lighter string, and for our pulley has some friction, we could reduce friction of pulley with oil. We could also reduce the friction of the axles in the wheels with some oil, but those are the improvements I can think of for my suggestions up here. The mark scheme also suggests that we could use an air track instead. So instead of having a rolling trolley, it's an air track with a gliding glider, which has much less frictional resistance as it slides instead of this rolling. That's another way we could improve it. Question 21c, part 1. Describe the energy transfer as the trolley accelerates on the desk. I've hinted at this already. What we've got is some weights that are falling down from a height and then pulling a trolley. The weights had some gravitational potential energy, which then decreases as it lowers, and this is transferred into the kinetic energy of the trolley as it's moving. So let's write that down. Gravitational potential energy of weights is transferred to kinetic energy of trolley. Question 21c, part 2. The trolley moves a distance of 86 centimeters along the desk. Calculate the work done when a force of 3.0 newtons is applied. Use the equation work done equals force times distance. Give your answer to 2 significant figures. Best way to approach this is to use the physics algorithm. So let's write down what we've got. We've got distance, 86 centimeters, force equals 3.0 Newton, and we want the work done. Writing down the variables like this helps us identify where we need to convert anything for units. So our force is already in our standard units of measurement for force, the Newton, but our distance is in centimeters. Now the standard unit of measurement for distances or lengths and things should be meters, and in order for this equation to work, our distance needs to be in meters. So 86 centimeters in meters is 0.86 meters. Now that we've got all of our variables to the correct units of measurement, we can put them into the equation and find out the answer. Work equals force times distance. Substitute in 2.58 joules. However, got to make sure we answer the full question. So 2.6 joules, rounding to two significant figures.